Welcome to my talk about the Jakarta EE Core Profile on virtual threads. I hope I'm online. So let's start. I will introduce myself first. My name is Daniel Katz. I work as a Helidon developer at Oracle. You can find me on the usual social networks. Well, the coolest one lately is the Blue Sky. So that's where I am residing the most lately. What we will be talking about, I prepared a little agenda so you don't get lost in all those thoughts. We will introduce the Helidon before, because I do Helidon, so you should know what it actually is. Then we will take a look at the Jakarta EE compatibility of our Helidon. We will take a look at motivation for using virtual threads, again in Helidon. What we did in the past where we didn't have the virtual threads, or not so long ago in the past. We will do a quick introduction to the virtual threads, take a look at some cool tricks they are doing behind the scenes and why they are so cool. And we will look at how we use the virtual threads in Helidon 4. That's why we are here, how we are actually powering all those cool Jakarta EE APIs in Helidon. And if we have a time at the end, we will take a look at this Achilles heel of the virtual threads and what to do with it. I hope I will get there. So we better start with the Helidon introduction, of course. So what is the Helidon? Helidon is a microservice framework. That's a little general, and actually the fastest and best way how to explain what the Helidon is that our main competitor is a Spring Boot. So we are a web server built to play really nice with Kubernetes. We are completely open source. All the source code of Helidon is available at GitHub, even though that we are backed by the Oracle. Unlike Spring Boot, Helidon keeps the number of third-party dependencies as low as possible. It's kind of comes from the corporate environment the core developers of Helidon are coming from, because we know that this is very important for the corporate users, as getting the approval for third-party libraries are usually being very complicated. And you don't really want to download half of the universe just to do a hello world. Right, so that's the Helidon. We do provide 3 default ways of packaging Helidon applications out of the box. The simplest one and the first one is a thin jar. It's a very small application jar just with your business logic. There is nothing else, just your code, accompanied with a lib folder for all the dependencies, even the Helidon ones. So everything is in the lib folder. Whoever did any C programming before, he probably know this model. So this is how by default is Helidon being packaged. This allows really nice Docker image layering. That's really cool, because you can orchestrate in your Docker image the layers with the lib folder and with all the dependencies and your business jar in a way that when you do some small changes in your business code, you don't have to push over the network into the remote Docker repository, the whole thing again, like you would have to with the fat jar, but you can push just the layer with your business code or with the libraries you have changed. So this is really cool for actual Docker deployments. The next one, that's even cooler one, is the J-Link image. J-Link image is that allows creating a minimalistic, custom-tailored Java runtime just for your application. So you kind of pack together the JDK or Java runtime with your application, and you don't need anything else. On your resulting Docker container, you don't need any additional JDK to run it. It will be everything nicely packed together. It understands the JPMS modules and does a tree shaking, so you can lose the parts of the JDK you don't really need. And of course, all Helidon modules are JPMS modules. We are very JPMS friendly, so it fits really nicely together. With JLink image and Helidon, I have tried to create a number for you. So I did this small hello world in Helidon and created a JLink image out of it, and I got 74% size reduction. That's really cool number to have on slide, right? So that was, for example, in my case, that was 339 megabytes. Together, it was 335 of the JDK plus 4 megabytes of the application, and it resulted in the image, JLink image size of 88 megabytes. So out of it, like around 60 megabytes was the JDK because of the tree shaking, the 4 megabytes was the application, and 23 megabytes was the CDS, that's the class data sharing file, which consists of some really cool optimizations you can do and make the startup of your Java application or Helidon application way faster, because the JLink really nicely fits together with the Leiden project. So if you are using latest JDKs, you can even do you can even pre-start and snapshot some preheated version of your application in this class data sharing file, and then start already preheated application out of it. So this is really cool. You can start quickly, and that's something that counts in the microservice environment. And the third one is even cooler. That's the Graal VM native image. You can create a native binary with super fast startup time. Again, this is ahead of time, so the compilation can take a little longer, but you get again a native binary which can be standalone in your Docker container, and it doesn't need any additional JDK to run. It has a more advanced tree shaking, which does not depend on the JPMS modules, so you get even better size reduction. So with my hello world, again, I try to give you a number. So I have achieved the 88% size reduction, which was again 339 megabytes, from which 335 was the JDK again, and 4 megabytes was application, and I achieved the image size of 41 megabytes. Nothing else you need in your Docker container, just this binary, and you can just run it and it starts immediately. It's really cool. All those options are easy to use with containers, and that's what we are targeting with Helidon. We have two flavors of Helidon. We have Helidon SE. That's not that interesting for all the Jakarta enthusiasts out there. It's a micro framework. There are no specified APIs, it's our own custom ones, and there is no magic, no injection. It's pure performance. You get it together with builders and lambdas, and you have all the wrenches and tweaks which you can turn on and off and tune your performance as best as you can. But it's for more senior developers who are not afraid to play with their stuff a little more. They of course need to invest more time into such tuning. Then we have second, which is Helidon MP, and that's very interesting for any Jakarta enthusiasts out there, and that's because it implements the micro profile. It's annotation driven. It implements Jakarta EE specifications like RESTful web services, the CDI and JPA and bit more, and it's very easy to use. Helidon MP uses Helidon SE under the hood, so you don't lose all that cool stuff. It's just hidden, so you don't have to really concentrate on. You can concentrate on your business code, and all that magic is done for you with the cool Jakarta APIs. We can compare it here. On the left, we have Helidon SE. That's the builder-like pattern with Lambda when we are doing very simple HTTP GET hello world resource with on the left with the SE flavor, on the right with the MP flavor. You can, I say resource, the Spring developer would say controller, of course. You can see that both sides are doing the same thing. On the right side, you can recognize that it's actually JaxRS, the RESTful web service from Jakarta EE spec. So you can take your JaxRS resource from your old WebLogic application and run it in Helidon, and it will be very easy to actually port such business code to Helidon because of all the specifications keeping the stuff compliant. And of course, Helidon integrates really well with WebLogic. That's because we are already the core of the Helidon developers are employed by Oracle. So we have certified integrations with WebLogic servers. So you can integrate, with WebLogic server cluster, and you can do some environments when both Helidon and WebLogic are running. You can integrate over JMS, over REST, good old-fashioned SOAP. You can use the OpenID Connect with the single sign-on thing, and the token will flow over Helidon microservices and over WebLogic cluster, and it will all work nicely with the IDCS. You can also do distributed transactions between Helidon microservices and WebLogic cluster. You can use LRA for that, or XA with our micro TX coordinator. But that's for another talk. That we will be here for hours. It's cool stuff. You may have already heard the big news that Helidon 4 is certified as Jakarta EE Core compatible runtime. So let's take a look at it. It doesn't mean that Helidon is some kind of a newbie within Jakarta EE ecosystem. Yes, previous versions were not certified as Jakarta compliant, but as you can see in this little timeline I have prepared here, since the release of the Helidon 1 at the beginning of the 2019, the Helidon MP implemented all the necessary specifications under the microprofile umbrella, including the Java EE in Helidon 1, and later Jakarta EE APIs in Helidon 2 and 3. Luckily, until recently, there was no direct intersection between the Jakarta EE specifications we consider as practical for microservice development and certifiable Jakarta profile. But Helidon has always been a standard-based microservice runtime, and that's no random coincidence. Helidon core team in Oracle actually consists of many seasoned committers to various Jakarta EE implementations. Just to list some of the implementations from my colleagues, there is a Toppling and Eclipse link for JPA, Moxie for JaxB, Jersey for RESTful web services. There is Jason for JSONB, Metro for JaxWS, JSON-BRI for JSONB, the Parson for JSONP, Tyrus for WebSocket, HK2 for dependency injection, and many, many others. With Helidon 4 MP and Jakarta 10, Helidon fully covers all the specs practical for microservice development, plus it partially covers others for the very same reason. But still, the Jakarta web profile, we already had like the subset of the large Jakarta EE platform was still too wide for us. We really didn't want to do servlets and faces and managed beans and stuff like that. But we we would still have all the goodies we needed, even not being certified for the whole profile, yet not be able to claim the Jakarta compliance. But in Jakarta 10, a new, slimmer, and for microservice development more practical profile came, and it was a core profile. A Jakarta profile specifically created for the bare minimum needed for microservice development. That's something we really, really like. So from already smaller web profile, which was still too wide for Helidon, just a few essential specs were cut out as a Jakarta EE 10 core profile. Profile tailored specifically for microservice development, as it seems to us at least. You can notice that CDI has been split to CDI and CDI Lite, a more build time friendly subset of the CDI spec there, but otherwise it's just a subset. And microprofile 6 took it on pretty fast and moved from the dependency on the several Jakarta EE specs to a single Jakarta EE core profile, therefore aligning with Jakarta. And this is simplifying the situation to all the runtimes and libraries for microservice development. Situation is much more understandable for our users, and the relationship between Jakarta EE and microprofile is clear. Again, we can compare how Helidon 3 implemented several standalone Jakarta EE specs to be microprofile 5 compliant. This was a little complicated to grasp and explain, because even creation of this slide required extra effort to check which specs are required and belongs where. So you have to be really careful what the microprofile, which version depends on which version, and so on. With Helidon 4, which is doing the same while being Jakarta EE 10 core profile compatible, explaining the microprofile Jakarta EE situation is very, very obvious. The Jakarta EE core profile making a base platform for other microprofile specs, that's very easy to understand and very easy to explain to our users and customers. It is still very similar to the previous situation though. As you can see, we are just implementing newer versions of all those separate Jakarta specs as we did before, but the relationship between all those things is really clearly defined and better. This time, we can proudly say that we are Jakarta EE compatible runtime. Because of the new Jakarta EE core profile and microprofile 6 alignment with Jakarta EE 10, the whole concept gets way simpler to understand for our users and even for us as the developers. And that's not something that comes really cheap, right? It's an assurance for our users that their Helidon MP-based application won't be bound by a vendor lock. It will be easy to maintain and upgradable to new versions of Helidon. And if someone doubts that, we can simply send them to check that Helidon is a Jakarta EE core compatible runtime, because we are just listed on the Jakarta EE compatibility list, which is cool. And our users have really clear assurances again, not only from us, but from the whole great Jakarta EE community this time, that their business code won't get old that fast as it could in any vendor-locked runtime, as their developers don't have to be a single runtime specialists, and support for the APIs they are using will be much wider than it could ever be from any single vendor. So now we covered how we are Jakarta compliant. That's something I'm proud of. And now we should talk about motivation, why to run Jakarta EE applications on a virtual thread. Because that is what we do for you in Helidon. We optimize concurrency. So let's take a look how and why. So the main problem we do solve in Helidon when you use the Helidon as a web server, the concurrency behind the scene is always very high. The users need to be able to call other systems from handlers we provide, like database, messaging, HTTP calls, and etc. Helidon server needs to respond really fast. So we are working hard for our users to save as much CPU cycles and memory as possible by utilizing resources as effectively as possible. And why is that optimization so important? Well, it's a cloud age now. Your managers can directly see how effective or costly your applications are. Less pods for same amount of work means less money you need to pay for your cloud provider. And Helidon gives you a great head start with that. At least that's what we are doing all the day. So the servers in general are dealing with some really heavy concurrency. The JVM specification doesn't actually state how Java thread should be mapped to operating system thread. Thanks to Ondro, he already talked about it in a few talks before. And so far, the Java thread was just a wrapper around the kernel thread, mapped one-to-one. It worked perfectly, but it was just a wrapper. But starting the kernel thread is very expensive. It's done by the actual system call. Every kernel thread created by JVM needs megabytes of memory. Again, Ondro already showed that in his talk, so it's really cool. We are kind of can explain it together. And the context switching is expensive, and it gets even more expensive with more threads already started. More threads you start, the more expensive is the bookkeeping of all that context switching. What have we done about it so far? We have been using thread pools, right? We have been reusing threads. We didn't start them too often. We didn't start too many of them. We have got used to thread pooling. That's how WebLogic done that for quite some time now. And also we have been avoiding blocking the thread. That also can help us to avoid the context switching, obviously, by keeping the threads really busy all the time, organizing the tasks for them in such a way that no blocking is really needed. So kind of taking on ourselves all the work that normally the operating system scheduler would have to do. Instead, we would have to do it in our business code. Not really nice, right? And all that's just to minimize the context switches. And how we have been doing that? With reactive programming. You like reactive programming? Let's take a look at it. Reactive programming is a way how to avoid blocking, thus avoiding the context switches, and that's the performance gain we get from that. The code needs to be asynchronous. Don't let your thread wait for something, continue to work on something else. Response or result will come by callback on someone else's thread. That means that instead of blocking, you just provide callback function. But by ditching blocking, we have lost natural back pressure. The thing when you block and your code just don't move forward, so you can't really receive or send something else, right? We can't control how much data comes back on those callbacks. The callbacks are executed on different threads by someone else. No one is waiting on anything. The order of execution is, well, there is no order, and all those price conditions are just waiting to happen. But luckily, we have reactive streams operators for callback orchestration. Reactive operators are implementation of reactive streams API. That is a set of APIs for orchestration of callbacks with built-in back pressure mechanism. That's how we are solving the back pressure issue. It is an attempt to bring order to the callback hell by a set of very, very strict rules. And is even part of the JDK since Java 9. You can find it in Java util concurrent package in a flow class. But while those interfaces seem to be fairly simple, the specification rules are ridiculously complicated. They are so complicated that when you try to implement the interfaces yourself, the IntelliJ actually warns you off. Don't implement it yourself. At least this is the screenshot from my IntelliJ from some time ago. Instead of implementing it yourself, it's probably better to use one of those already existing libraries providing reactive primitives with operators implementing reactive streams API. there is like the most famous one, the Eric's Java from David Carnong and a bunch of Netflix guys. There is Reactor, done also by David Carnong and Oleg Dokuka and other very clever people. There is Akka Streams, the service talk from Apple. We do have in Helidon our own operators, also contributed by David Carnog, and there is Mutiny from, you can note that from Quarkus, from Red Hat. They have little different builder-like API. It's kind of interesting API. So there is a lot of implementations out there. You don't have to implement it. You can just straightforward use it to orchestrate it somehow. Now that we have established that reactive operators help with this complexity of asynchronous code, how many of you do actually like it? You know, the working with the reactive operators. It's confusing at the start. It doesn't get really better. It's still a trap. The reactive programming has a steep, very steep learning curve. It's a maintenance nightmare. The debugging is really, really hard. The stack traces are practically useless, and blocking or obstructing code needs to be offloaded to extra threads anyway. Otherwise, terrible things are bound to happen. Just imagine that you will be trying to explain your reactive code base to some junior developer who has just joined your company. That's a task which is mission impossible, right? And don't remember, reactive APIs are viral. Once you use them, you have to propagate it further to avoid bogging. So it spreads through your code base just like the real virus. It's once you get it there, it will be very hard to get rid of it. Luckily, there is something better. Virtual threads. In September 2023, with Java 21 release, the JEP 444 delivered Project Loom. And Project Loom, among others, brings the virtual threads. Now you can choose if you want to use platform threads or virtual ones. Blocking operations don't cause expensive context switches. We can have a huge number of virtual threads, and it's cheap. The stack traces make sense again, and naive imperative programming, which you know so well from the Jakarta API, is safe and performant again. It's on par with the reactive programming. If the reactive programming is done right, it usually isn't, so you are usually faster with virtual threads anyway. The virtual threads have the same effect for avoiding the context switches. It's like reactive programming has, but it doesn't pollute your code anymore. It happens behind the scenes. Before somebody asks, there is usually 1 or 2 questions like that. We had something very similar in Java before. It was called green threads. Those were also user threads working on top of but working on top of a single physical thread. Back then, the computers had usually a single CPU, so there was exception on Solaris JDK, but that's a different story. But it was replaced eventually by OS thread abstraction to allow the real multi-threading instead of multiplexing, because that was what the green threads were doing. And it was just multiplexing over a single thread. It was simulating parallelism. It wasn't the real one. The virtual threads, on the other hand, always use multiple physical threads as a carriers. So you can squeeze power from all your cores in your computer. And this is really, really powerful. It's also more complicated for implementation, right? But that's not your problem. Unpark of the virtual thread actually schedules continuation to be run by one of the carrier threads. The scheduler here is actually a forjoin pool. Again, thank you, Ondro, he already mentioned that. And thank you, Doug Lee, for giving us a forjoin pool, because Doug Lee obviously saw already when we have been ditching the green threads from Java that we will have something else than just the physical thread abstraction. Those are continuations under the hood. For example, let's see how thread sleep actually yields and park continuations. So let's look inside this Java-lang thread class. Everybody knows that. And notice how sleep method does something else for virtual threads since Java 21. If you inspect the virtual thread sleep nanos method, and follow the rabbit a little deeper down the hole into the park nanos, you are going to find yield continuation. So here we are. Those are continuations in Java. What is actually happening when continuation yields? The continuation is unmounted from the carrier thread, so it can serve another virtual thread again. The carrier thread needs to, always be working. It cannot stop, otherwise it would be rescheduled by the operating system scheduler, and we want to avoid that, right? So this time it's done for us by the virtual thread runtime. Normally, when this context switch is managed by the scheduler over physical thread, the whole large thread stack needs to be moved around, and that, as we know, could be pretty expensive. There are those megabytes of data you need to move around the registers, and that's really expensive. And if you have more threads, it's even worse. With virtual thread scheduler, it is done a little differently. It's called freezing and towing. When continuation is unmounted, the continuation part of the stack is being saved for later. The process is called freezing. When continuation is mounted back on the carrier thread, its stack is being copied on top of the carrier thread stack. The process is called towing. As you can see already, we are moving around only the part of the stack which relates to the virtual thread. We are not moving the whole stack of the whole thread from the depth of the JDK, right? We can try to demonstrate the stack manipulation with this small server example I have prepared for you. When virtual thread gets blocked in the read socket method, there is this endless loop I have here, which just always get blocked on the read socket method until the data arrives on the socket. It's the usual case, and we are just being blocked until the data are available. So you can see here the virtual thread 999, which I'm trying to make it look like there is thousands of them, on this carrier thread 1, that the stack I have left visible only the part which is interesting for us. That's the virtual part of the virtual thread ones. And you can see that when we are hitting the yield continuation method, continuation part of the stack is freezed. Oh, the animation works, cool. So now we have we have saved it for later when we need to mount the virtual thread back on the carrier thread again. When our continuation gets mounted again, it's not the whole stack is copied back. There's another optimization here, but just a few frames with a return barrier. So we have moved only the part of the stack which belongs to the virtual thread, and we will be moving back even shorter part of it, like this. The return barrier is lazy substitution which guards the return address of the read socket method. So when the return barrier is reached, more frames will be loaded lazily in my animation. And now we can see that we have another frame available. And this way, we can actually rotate in this endless loop and moving around only this sensible part of the stack, not all of it, just the part which is really interesting for this endless loop. That's because the virtual thread scheduler actually knows way more about the context, what is happening in the JDK than the operating system scheduler. We just know if it's Java runtime or some binary. It just works with the system threads and moving them around. So it cannot really differentiate which part of the stacks are relevant or not. But the scheduler we have now in the JDK, it actually can. Tricks like that make virtual threads so effective. And this is not the only one. There is way more of them. Oh, I have more animation, sorry. There is way more of them. There are other super cool tricks like the frames which are being frozen for a longer time, get goes under the comprimation process, that that it doesn't take so much memory and stuff like that. It's really cool. And if you want to know more, you can learn that from more clever people than I am. Like from this video, you can find it on YouTube. It's called Continuations Under the Covers. It's from Ron Pressler's talk on JVM Language Summit, and he's explaining the tricks like that there, and it's really way better explained than from me. But I try to give you some notion why are virtual threads so cool. It's not just that it somehow works. There's a lot of cool things happening under the sheets that you don't need to know about, but that makes them so fast. Now we can take a look how Helidon 4 puts the virtual threads into the action under all those cool Jakarta APIs. So what we did in Helidon 4, well, we got rid of all the reactive stuff from web server. We got rid of Netty, the well-known and very powerful library for working reactively with sockets, or asynchronously, that's a better term, with sockets in Java. We have created a brand new web server, fine-tuned for virtual threads from socket up, all the way up to your Jakarta RESTful handler. The removal of Netty allowed us to get rid of all the reactive APIs in the process. Our brand new web server with secret code name Nima is clean, really fast, and optimized for virtual threads from ground up. This is actually very important, because just doing the retrofitting wouldn't really work for us, as all those optimizations we have done so far would be with different contention we get with the virtual threads would actually be working against us. You can see here on this slide how Helidon MP APIs did not change at all. Just Helidon SE APIs are imperative, and blocking code is embraced in Helidon 4. The imperative Jakarta RESTful APIs didn't change at all. The CDI bean is still the same. It's very same, sorry. And now we will take a look at the Helidon 4 SE. There is actually a difference, because we have been switching from the reactive API to the imperative one. Here you can see the comparison between Helidon 3 and Helidon 4. On the left, there is reactive API. This is very simple. HTTP GET method handler, which calls another HTTP client, some other endpoint, and when it gets the response, it does some business code. In this case, it's just doing the uppercase, and it sends the response asynchronously from the callback, of course, because it cannot be blocking anywhere. You can see all those callbacks here. If you would try to debug this, you will be jumping, from there to there, because those callbacks are certainly not being invoked in the order you would expect. And you have to actually understand reactive streams really well to know how to debug this thing, right? On the right side of the slide, there is Helidon 4, the imperative API we now have for Helidon SE. And as you can see, it does the same thing. It's just blocking until it gets response from the, this time, blocking client, HTTP client. So if you will debug this, you will be actually debugging from up to down, jumping from line to line. When it's blocking until it gets the response. So on the getString method, you will be standing with the debugger until you get the response. So it's easy to debug. It's easy to reason about it. It will be very easy to explain it to that junior developer who just joined your company. It's way easier than the one on the left side, right? Again, Helidon MP has Helidon SE under the hood. So you get all the goodies in the MP version 2. And as you can see, here is the comparison of Helidon 3 MP and Helidon 4 MP. This is the RESTful API, Jakarta RESTful API here. So you can see it is very same. It's the same. The imperative Jakarta RESTful APIs didn't change at all. And that is the beauty of the Jakarta EE specification not falling for this reactive hype in the last years. Your business code based on JAX-RS can switch to virtual thread-based server without the hassle. The Helidon MP was always imperative, and it will be even more. Now you just get way faster with no change really needed. There is no reactive layer anymore. This is very important to point out, so I have another slide for it here. And when we say that we use the virtual threads, there is no offloading, there is no retrofitting. It is the virtual thread per request in a web server built specifically to work best with virtual threads. Also, as we are optimized for Java sockets with virtual threads, we get faster and faster each time new release of Java arrives. And as a bonus, we got rid of a lot of security issues coming from Netty. Now we can create our own, right? So what we did differently in Helidon. Our web server is built and tuned specifically for virtual threads. You can't turn off the virtual threads in Helidon. It's not hacked in, and it just won't even work with the physical threads anymore. Work with sockets is specifically tuned for the virtual threads. It is like very important part of all the work we did. We have worked on that in close collaboration with Loom developers. We don't support virtual threads by offloading to them from physical thread workers. And we didn't just retrofit it existing worker pools. That just doesn't work, as that contention in the web server is quite different now, and all the optimizations are suddenly working against you. Web server replacement brought significant simplification of our code base. That's really cool for us, the developer of the Helidon. The virtual threads are not just an abstraction layer. We use them for the whole story. The blocking API is not just a nice facade. It's the virtual threads are used from the very bottom up in Helidon. This way, you get performance on par with reactive runtimes, with easy to use blocking APIs powered by simple and pragmatic runtime. And now we have time, that's cool. So we can take a look at the Achilles heel of the virtual threads, the pinning. Everyone heard about the pinning, it's super scary, right? So we will take a look at it, what it is and what it does. There is a known issue with virtual threads when the carrier thread gets blocked together with the virtual thread. This can happen, for example, when Java synchronize is used for blocking, or when locking is done behind the JNI interface. There is some mutex lock somewhere in the native library you are using, and it will just lock. It will just block your carrier thread. As you can see on this really cool picture I have created for several hours, what happening is that that one carrier thread that the work pool of your scheduler uses is not available anymore to all those unscheduled virtual threads. So there is less resources to use. You are wasting this physical thread. It will probably trigger the operating system scheduler. There will be more context switching, and so on. So again, usual suspect is synchronize. It's not always harmful. Short-lived memory operations are not harmful at all. If, for example, if you take a look at the concurrent hash map, there is synchronize in it, and it works really well with virtual threads. It just needs to fit under those default 20 milliseconds, which is the difference between pinning and not pinning. That's so it's not always a bad thing. In case of the pinning, the carrier thread pool compensates by spinning additional carrier threads. So this leads to performance degradation, but it still works. It doesn't stop working. It's just you will get slower. The reentrant locks don't cause the pinning. Those are virtual thread friendly. So let's take a look at this really simple example. We will do simple sleep in the synchronized block. As we already discovered a few slides back, the sleep is actually yielding continuation on virtual thread. But this time we will synchronize it, so it will get blocked before the sleep is even reached. So it couldn't yield, and because synchronize doesn't yield, that's a problem, right? There is no alternative logic available for it. So we have two options how to detect the pinning here. Notice that we are sleeping for more than 20 milliseconds. That's important. So the first option for pinning detection is with JDK trace pin threads system property. You can see exactly where the pinning happened on the printed stack trace. You can see it's on the line 8 in the mine.java class. You can set the property to short value that will print just the problematic frames and so on. But this approach is not really recommended for use with Helidon, at least not by us. Printing to the system out with this type of contention can be quite problematic, and we've seen some ugly issues with that. I think the worst ones are already fixed, but still you don't want to print into the system out. The better option to detect pinning is with Java flight recorder event, that the JDK virtual thread pinned event. It is very easy to use, again, as it is enabled by default for operations that takes longer than 20 milliseconds. That's the default threshold when we consider blocking of the carrier thread as a pinning. We can enable it explicitly in our example here on the slide and dump the JFR recording to file to inspect it later. In the recording, we can find the same information about where the pinning crime is being committed. So it's very same. But again, it doesn't always help. The fixing the implementation, obvious help could be fixing the implementation to be more virtual thread friendly, therefore replacing the synchronize, offloading to the physical thread. That's like universal solution for legacy libraries, for JNI usages with those mutexes we cannot really work with, or for some heavy CPU usage where virtual threads are not really that effective. So I will just move here. Synchronize is fixed in Java 24, and you can try it out later. It's still better than reactive, and I hope you liked my presentation. Thank you.